Hello everyone, welcome to part 2 of molecules and ions. Yep, you guessed it, it's ions. Now, we left it at kind of an important page because you can discover or determine the type of bond between any atoms just by their position in the periodic table. So that's why location, location, location when trying to determine a bond, okay? So in the first part of the packet we saw that if I pick anything from the top right, something with what we say has a high electronegativity, right? We'll talk about that trend later, but just for now, anything from the top right, including hydrogen, if any green one bonds to any other green one, it will make a covalent bond, okay? It will form a molecule. So associate covalent bonds with molecules, and anything bonded to anything else in the green area. For example, CO2, carbon and oxygen stuck together, was a molecule. Now we're going to move on to things like table salt, which are ionic, and again, location, location, location. If I mix any of these purple elements, okay, or atom types, which are metals, with any of these green ones, which are non-metals, and that line divides metals from non-metals in the periodic table. It also divides low electronegativity from high, which we'll talk about later. But anything from the purple side here with anything from the green side will make an ionic bond or a giant ionic compound, okay? So those two things go together. So it's all about location, location, location. From now on, when we talk about atoms making ions, it'll be a lefty and a righty stuck together. As we'll see, these will make plus. So for example, Na will make a plus ion, and Cl will make a minus to make NaCl, table salt. Okay, so that's the golden rule. A lefty and a righty makes an ionic bond. All right, and therefore an ionic compound. So let's talk about it in kind of a simple way first, and then get into the nuts and bolts. So what's an ion? Very basically, we talked about it in the flow chart. An ion, and we'll talk about atoms first and molecules later, but an ion is an atom, which we'll talk about first, or a molecule that has either a negative, my abbreviation is minus VE, or a positive plus VE charge. That's essentially what an ion is, okay? Now, just right up here, plus equals what we call cation, minus equals an anion. So if I say, hey, cations, plus ions, Na plus, stuff like that, anions, minus ions, Cl minus. All right, so atomic ions. Now, this is where it gets interesting, okay? So, I want to show you a picture first before we fill this in, okay? And I'll flash up a nicer picture when we're done on the screen, just to compare, okay? So if I take, for example, Na, right? Na, if we look in the old periodic table, and you know, periodic table is your friend, right? Na is element number 11, which means it has 11 protons, right? So I'm going to give it like a plus 11 nucleus there, right? And so if I'm thinking about an atom, it has 11 electrons because it's electrically neutral, right? Now I'm going to make sodium chloride, table salt. I'm going to bang together an Na and a Cl and they'll stick, right? So I'm going to have my Cl down here, right? If we look at Cl, number 17, right? Oh, number 17. So 17 protons, 17 electrons. So I'll put a plus 17 nucleus, if you like, and then 17 electrons. All right. Now what happens is when you make an ionic bond, you make ions, right? And they stick because one's plus and one's minus, right? So you bump these atoms together, and what happens is sodium, because of its weak electronegativity, again, we'll get to that later, that's electron stealing strength essentially, right? So it's very weak. This guy's really strong, okay, and an electron will jump across. That's the process of ionization. Ionization is the process of making ions. There are no ions just existing in nature. They have to form as a pair through collision and electron exchange, right? Then immediately once they formed, if you think about it, what do you get here? So you've got Na. Now it's still sodium because it's still got 11 protons. Remember, the identity is how many protons, right? So it's got plus 11 in the nucleus, but how many electrons now? 10, right? Because one was stolen, if you like. So 10 electrons. What's the net charge? That keyword net. The net charge is one more plus and minus, plus 1. And we write that as Na plus, right, for shorthand. But that's your sodium ion. It's a +1 because it lost 1 electron, right? So maybe let's write that up here, okay? Metal ions, talk about atoms first, okay? Atoms that are metals, as we just saw, lose electron or electrons to become net positive and get it right, cations, right? Cations. All right. So metals lose electrons through ionization to become net plus. They make a cation. On the other hand, where did that electron go? It doesn't just float off. It's a subatomic particle. It can't exist by itself, right? It jumps onto another atom to make a stable ion, right? So it's still chlorine in the center there. It's +17. But it gains 1 electron, so that's 18 electrons. What's the net charge? 18 minus 17 plus, net -1. We call that a chloride ion. We change the name of the minus sign, more on that in a second. Sodium ion, chlorine becomes chloride ion. Okay, so that's how it works. So non-metals, if you like, green ones from our previous, so anything in the purple area, sodium makes a plus, chlorine makes chloride, it's a minus, metals go plus, non-metals go minus. This is the table of the atoms, right? It's what they do that's important. So these make plus ions, these make minus ions. All right, there we go. So non-metals, atoms gain electrons. Some will gain 1, 2, possibly 3. Okay, we'll talk about more in a second. To become negative anions. So it's the chloride anion, sodium cation. All right, hopefully that makes sense. I'll throw up a nicer slide from the notes, and if I, where will I put it? Somewhere up here, right? Do that YouTube thing. Okay. Actually, I'm going to be on your right, so over here somewhere. Okay. All right. Now, very, very poor joke. Very poor joke. Okay. 2 atoms walking down the street. Oh no! Oh no! I think I lost my electron. You positive? Yeah. No. Told you it's bad. Okay. All right. Moving on. Now. Interesting. Okay. So I asked you to memorize very few things in the course, and that's true for pretty much all chemistry courses. But there are some things you must learn, and it's a bit like when you learn your ABCs when you're a kid. You need to know your alphabet so you can put letters together to make words, right? Same kind of thing in chemistry. You need to know your ions so you can put them together to make ionic compounds, right? So Na plus and Cl minus stick together to make sodium chloride, for example. Okay. Now, it turns out the number of ions you choose for plus and minus depends on their charge. So you've got to know the charges of the ions, right? Okay. So if we look in the back of the packet, last page, maybe I'll keep this on the side because we'll keep coming back to it. This is a chart of the common ions. Now, there's probably a couple of hundred ions out there in nature. I'm asking you to memorize a small fraction of that, okay? And to be honest, it's not a pure memorization job because a lot of this relates to the periodic table, which we'll show you, okay? So my advice is, make a couple of copies of this chart. We'll talk about how to memorize facts and figures later with a little trick. All right, now, so if we look at our periodic table, now here's a neat trick. So what I want you to do, get your periodic table. Okay, let me use a different colored pen. This is what's called group 1. So the hydrogen group is group 1, the beryllium group is group 2, and then we're only going to go up to 20 for now, right? And so we're going to skip the middle. This is important, right? The boron group is group 3. This is old school, yeah, okay? You guessed it, carbon's group 4, and the group number, if you like, is always written in Roman numerals, which we'll talk about more later. You guessed it, 5, 6, 7, 8. So, for example, nitrogen heads group 5, oxygen heads group 6, okay? The group is important for chemistry, and we'll talk about why in another packet. But for now, just know these guys are in group 1, these guys are in group 2, 3, 4, 5, 6, 7, 8. Okay. Now, turns out, if we look at our sheet and we kind of superimpose it with the periodic table, okay? Hydrogen, lithium, sodium, potassium, hydrogen, lithium, sodium, potassium. Anything in group 1 will make a +1 ion. So the group number is the same as the ion charge, okay? So when atoms make ions, if they're in group 1, they make a +1 ion, right? So lithium plus, you can just name them, right? Sodium, just go through. The common ones, potassium, those are the common ones, but all of them do it, okay? So anything in group 1 will make a +1. These are the things we see commonly in lab and questions and things, okay? All right, so whilst we're here, group 2, take a wild guess, right? Group 2 makes +2 ions. Move this across so you can see. So there they are, magnesium, calcium, strontium, barium. All those are in group 2 of the periodic table. Okay, there they are, okay? Beryllium also, but it doesn't come into play much in terms of questions. So these are the common ones, particularly magnesium, calcium, and barium. These we see all the time in lab. Okay, but anything in group 2 will make a +2. All right, these I haven't asked you to memorize all, but hey, it doesn't matter. Group 2 makes a +2. So group 2 +2. Let's do the classics. Ions, right? So we'll do from our list magnesium, calcium, barium. Those are the, you know, the big boys, so to speak. Those are the ones that count, but everything in group 2 makes a +2. Now it's interesting, if we remember our chart from before, I can find that real quick, okay? So this is group 1, this is group 2. As we go towards the right, okay, we get closer to the border, so things become less metallic. That means they make ions less prevalently, okay? So things on the border, there's not so many. So not everything in group 3, if you look at it, will necessarily make a + ion. And for our purposes, that's nice because for group 3, only aluminum, okay? So aluminum in group 3 makes a +3 ion. So aluminum +3. All right, so there are your ions, right? For groups 1 makes +1, group 2 makes +2, and group 3 just aluminum makes +3. Now interestingly, we said chlorine makes, where's chlorine? Well, first up, the last column is the inert gases, right? So no chemistry, they're just atoms in nature, they don't do anything. So chemistry really starts in column 7 if we kind of go backwards, right? And we saw that chlorine made a chloride -1. That's right, so everything in group 7, and if you think, oh, just, you know, start chemistry in column 7 and go backwards, everything in column 7 makes a, if we look at our list here, do it backwards, -1, right? So these guys are all here, okay? So column 7 makes a -1 ion, all right? 5, 6, 7, -1 ions. So F- is fluoride. Minus ions change their name from the atom. Chloride, bromide, and iodide. Those are on our list to learn. There they are. Okay. Group 6, step across one more. Group 6, headed by oxygen and sulfur. Now again, we're getting close to the middle here because we've already kind of stepped in one from the edge extra because of the noble gases. So only 2 do it, oxygen and sulfur. Can you think of what those ions might be called? Sulfide, right? Now, in the same way, oxide and sulfide, we go +1, +2, +3 in from the left, we go -1, -2, -3. So as you go towards the center, the magnitude of the charge gets bigger, okay? So, -2 ions are in group 6. -2 ions, there's only 2, 2 minus oxide, 2 minus sulfide. All right, nearly there. So almost right in the middle. Column 4, if you like, is in the middle, doesn't make any ions, right? But hey, right next to it is column 3, which is just 1 aluminum, and then column 5, which is, let's look at our list here. -3, N3 minus is nitride. That's column 5, so -1, -2, -3, column 5, just the one at the top, makes a nitride ion. Okay. -1, oh, sorry, -3 ion, N3 minus. Okay, so those are the ones, just using the periodic table, just remember the golden rule, column 1 +1, column 2 +2, column 3 +3. Walk it back from the other side, column 7 -1, 6 -2, 5 -3. Okay. Now, kind of alluded to it a little bit. Ions don't really keep their name, right? They actually change their name, all right, if they're minus, yeah? So it's a bit like getting married in the 1950s, right? So back in the day, who changed their name? It was the girl, typically, right? So chlorine became chloride when they bonded, right? So when they got married, right? So it's a kind of crazy way to think about it. So let's just think about that as an analogy, right? So metals, though, keep their name, right? So sodium atom, this is a sodium atom. What does it make? Group 1 makes +1. Na plus keeps its name when it makes an ion, when it makes a bond, right? Sodium, ion. So sodium keeps its name. Chlorine became chloride. Oh, the sodium chlorides, what a beautiful couple, right? So that's my no charge, right? So that's I write it in caps so you can read it. Chlorine atom becomes group 7, makes a -1, IDE, ion. Okay. All right, so the chloride ion changed its name, chlorine to chloride. Okay, and that's true for all atomic minus ions. So chlorine chloride, oxygen oxide, sulfur sulfide, nitrogen, an atom, nitride. All right, okay. Moving on then, so try these, right? So try magnesium and oxygen, atom and ion. Okay, so magnesium, atom, group 2 makes +2. Periodic table, always have the periodic table handy, right? So you can kind of look at what column it's in. Okay, magnesium, column 2, +2. All right. Magnesium ion. Oxygen, well, let's just do the atom first. Oxygen atom. What charge does it make? Well, we're stepping in one more, so group 6 makes -2. That's called an oxide ion. So we change the name to put "ide" on the back for minus ions. All right. So that's how you name ions and get their formulas, right? It's all about where they are in the periodic table. Okay. So here's a truism, right? So if you think about it, table salt doesn't have any net charge. You pick up a rock of table salt, it's got no charge, right? No static discharge or anything like that. So the pluses equal the minuses. So for every plus, Na1, there's a minus, Cl-1, right? And they bond, so the charges cancel, right? Talk more about that in a second. All right, so you can make any ionic compound literally by combining any plus with any minus as long as the charges add up to 0. We'll practice that in a second. But naming them is even simpler, right? So like, you know, oh, here's the beautiful sodium chlorides, right? You can name the compound based on what's inside. So Na plus, Cl minus, sodium ion, chloride ion. Just run the two names together. Now, if you think about it, metals are always going to be on the left of the periodic table, so they go first, yeah? It's just like with molecules, right? So whoever's bottom left goes first, yeah? So why is sodium chloride, not chloride sodium? Because it's sodium ion +1, chloride ion -1, stick together, right? And then you just run the names together. We don't have to do monos, dis, and tris, because if you think about it, the charges have to cancel, so we know how many are in there, right? So the big difference between molecular and covalent, the molecular and ionic compounds is there's no dis and tris and things like that in ions, because you know how many's in there because of the math, right? But with molecules, there is no math, there is no charge, so you have to tell me. So that's why it's dihydrogen monoxide. Okay, all right, so try this one. So sodium chloride, just run the names together, sodium ion, chloride ion, nice and easy. What's that? What's that? Hopefully you got it, nice and easy. Lithium ion, fluoride ion, like flower but switch. U and O, all right. Okay, so there we go. Now, just told you the magic trick a second ago, right? The magic trick was you can combine any plus with any minus ion, and as long as the charges add up to 0, or charges cancel if you wish, it's a real compound, okay? And I'll go get it from the stockroom at work. Okay, so let's look at this, right? So maybe there's not a super lot of room here, okay? But if you think about it, I've got 3 pluses and 3 minuses, therefore there's 9 possible combinations. So let me get a piece of paper, and I'll do the first one with you, okay? So let's do lithium compounds. And then we'll do calcium compounds. And then we'll do aluminum compounds. Now you can try and squeeze this in on the sheet, that's fine. but it's not really a lot of room, okay? So let me do the first one. So maybe I'll leave the ions so I can see them like that. So lithium, names and formulas, right? So I'm going to get a lithium. Now, very, 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 very important. I told you, right? Never leave the charges in any formula. If you leave the charges in, I know you need the charges to do work. You need to make the charges add up to 0. But if you leave them in, technically they're not cancelling, right? So here's the trick. Do the math underneath, then erase it. Use a pencil, right? So lithium makes a +1 ion, right? There it is. If I mix it with chloride, it makes a -1 ion. +1 -1. That cancels. It cancels in a 1-to-1 ratio, right? So forget about that. Now we'll just get rid of that, right? That's the formula. That's what you'd write on the test. Alert. That's what you write on the test. Some people are going to put the charges in the formulas and they're going to get 0 out of 20 on this test question, right? You can't leave the formulas in. They're actually something else. In chemistry, they're called an ion pair. Forms at the surface of a battery electrode, which is nerdy, but whatever, right? Okay, so what's the name of that? Name it. Lithium chloride. Fair enough. Now that's an easy one to start, right? That's an easy one to start. But when you look at these different charges up here, some of them aren't easily cancelling, are they, right? Some of them aren't easily cancelling. So let's look at a fiendishly difficult one. Let's do aluminum oxide, right? So aluminum oxide, I've got aluminum, which is a +3, and an oxide, which is a -2. They do not cancel 1-to-1. Do not cancel 1-to-1. So here's the big trick, right? We can actually write the name first, because the name's always going to be the same. Doesn't matter how many are in there. Aluminum oxide, right? Just run the two ion names together. All right. Now here's your trick, right? This is a +3, that's a -2. What's their lowest common multiple? 6, right? So I want a +6 over here and a -6 over here. Hey, how many 3s make 6? 2. So I need 2 of these things. How do you represent the number of things in a formula? A subscript. So 2 plus 3s. Fair enough. Now, -2 times 3 is 6, right? So I need 3 of these. I need 3 of these. So 2 plus 3s cancels 3 minus 2s, and then erase all that, right? And that's the formula of aluminum oxide. All right. So give it a shot. Give it a shot. Give it a few minutes. If you write small, you could maybe squeeze them in there, right, with their names. Okay. But I'll do it on the sheet. All right. I'll put C sheet. Okay. So you're back. Let's do the lithium compounds first. So lithium is a +1. The next one over is oxide, right? That's a -2. So maybe we'll do the math for this one. That's a -2, that's a +1. This is the question I have for myself in my head. How many +1s cancel a -2? Well, obviously 2. 2 +1s. That's still called, cross that out, lithium oxide, right? All right. Okay, it has to be 2 Li's and it has to be 1 O because that charges that up to 0. That's why we don't have to say dis and tris. That's why, right? So no dis and tris in ionics. Again, why? Because there's only one ratio, 2-to-1 in this case, that works, which makes the charges add up to 0. Finally, can you do the last one? Hopefully this is good by now. This is going to be lithium nitrate. That's going to be a 3-to-1. Okay. I've got literally 2 minutes left, so I'll quickly go through here. Well, actually, no, I have the power of editing. I keep forgetting. Calcium compounds. Calcium. Let's run through. Move that up. Get it perfect. There we go. So calcium, chloride. That's a +2, that's a -1, so I need 2 of them. Hope you're getting the hang of it, right? Okay. Next one, nice and easy. Calcium oxide is the formula. Why? +2, -2. 1-to-1 ratio, +2, -2 works, okay? Finally, calcium nitrate. This is like the evil twin of aluminum oxide, right? Because that's a +2, that's a -3. So I need 2 3s are 6, so 2 of those. And 3 2s are 6. There we go. Calcium nitrate. Okay. Down here, aluminum, let's just do the name over here. We did aluminum oxide earlier, right? We're going to do aluminum with chloride, aluminum with oxide, and aluminum with nitride, right? So let's just maybe put the names in. Aluminum chloride, aluminum nitride. Let's do the formulas, all right? So chloride, +3, -1. How many -1s cancel a +3? 3, yeah? Actually got a little bit more time than I thought. We're at 25 minutes. We've got time to finish this, right? So +3, -1, 3 of them. Aluminum nitride, now be careful, that's an IDE, right? Atoms have the IDE, and you've heard of nitrate, and a little bit of knowledge is a dangerous thing. A nitrate ion is a molecular ion, which we'll get to in a couple of pages, all right? So atom N3-, nitride ion. So that's a nice easy one. That's a +3, that's a -3. That's good to go, right? That's good to go. So that is the formula, aluminum nitride. Okay, so we'll stop there. I'll be back shortly, in the words of the Terminator. Take it away, Arnie.
I'll be back.
Welcome back. Have to excuse my indulgence there. Okay, so this is where we left it. Now let's go back to the ion chart real quick. So we've talked about the ions you have to learn, and about a third of them you can just kind of look at the periodic table. Group 1 makes +1, group 2 makes +2, work it backwards, group 7 makes -1, group 6 makes -2, and then in the middle, group 5 -3, group 3 +3. And as you get towards the center, less prevalence towards ion formation, so there's less ions kind of from the middle. Okay, the periodic table. That does leave us with a bunch more. Okay, the next ones we're going to look at are molecular ions, all right? So things maybe you've heard of phosphate, sulfate, carbonate, and yes, there is nitrate, which is a molecular ion, okay? So these are molecules with a charge, mostly minus, but 1+ ammonium. Okay, so let's take a quick peek back, all right? So you've got to learn those. Now, how do you memorize kind of cold facts, right? Well, if you've taken maybe an anatomy and physiology class, maybe you learn the bones of the hand or something, I mean, you've got to kind of just memorize through just repetition, right? So flashcards and things like that. You know, back in the day before Tinder, people just come to your house now, right? You actually used to go out and have to meet people, and you go to a bar and, you know, someone will tell you their phone number and you kind of say it in your head 100 times so you remembered it, right? So repetition means you learn something. So if I was going to learn those ions today, what would I do? Well, I just print this out a bunch of times, all right, make copies and just put them around the house where I look, you know. As a proud middle-aged man, what do? Watch a lot of TV, so I sit on the sofa or lie on the sofa, watch younger males throw or kick balls at each other, right? Go Liverpool, all right. Occasionally rise from the sofa, go to the fridge, open the fridge, look inside, close the fridge, go back to the chair. Okay, so if it was me, I'd put, like, you know, a sheet on the sofa, by the sofa, a sheet by the TV, and a sheet by the fridge. Okay, but for real though, when I did this kind of as a student, when I was in high school, I had to learn organic chemistry, the pathways of organic chemistry, and there's like a aliphatic scheme and an aromatic scheme, and you can make these maps, right? And one looked kind of like a boat, so that was the boat map, and one looked like a windmill, that was the windmill map. And I kind of took down the posters from my bedroom wall and wrote out these reaction maps on the other side and put them back. Okay, so I'd fall asleep reading about organic chemistry, I'd wake up and the first thing I'd see is organic chemistry, and you guessed it, screaming up in terror in the middle of the night, organic chemistry. But I still remember features of that today. Okay, take a, let me think, right hand side, aliphatic, take an amine, boil it in HCl to make a nitride. Still there, 40 years later, now 30 years later. Okay, so naming molecular ions. Unfortunately, you've got to know the names and the formulas of the molecular ions. There is a small trick, which I'll show you, okay? There is a small trick, which I'll show you, but we have to know the names and the formulas of the molecular ions. Everything else is the same. The math, actually, is just the same. It's just we use a different formula. So it's a larger blob with a charge, not a small blob like an atom, okay? So, as we mentioned, there's only one molecular ion that's plus, ammonium. Now, what I like to do with molecular ions is put the molecule in brackets and then give it a charge. It's like saying, hey, put some oranges in a bag, and the bag of oranges has a charge, not the individual oranges, all right? So count the bags, not the individual oranges, right? So we think, hey, that's one ammonium molecule which has a charge, right? So it acts just like Na plus in terms of the math, right? It's got a +1. How many of these blobs do I need, right? Okay, so ammonium's +1. There's a very few, the rest of them are minus ions, there's a very few without oxygen, okay, and they usually have the same consistent IDE-ide ending, right? So when I say few, one or none, right? So the classics are OH minus, that's hydroxide. These are on your sheet down here, right? Okay, and CN minus, cyanide. So hydroxide, cyanide, one oxygen, no oxygens, we're good to go. Okay, so these are molecules, they're small molecules, 2 atoms, right? 2 atom molecules, but they are molecular ions with ide endings. Okay, so that's the 2 ides, hydroxide, OH minus, cyanide, CN minus. Okay, then most of them, to be honest, are what we call larger oxyanions, right? They have lots of oxygen. Okay, so here's a little thing. Do you remember Pac-Man from years ago? Right, here's Pac-Man. You ever played the game Pac-Man? What does Pac-Man do? Pac-Man eats stuff, right? All right. So I'm going to have Pac-Man, and I'm going to have Pac-Man wearing an S shirt, right? Super Pac-Man, right? So sulfur 8 oxygen, SO4 2 minus, sulfate, ATE. Okay, so the 8s have lots of oxygen. That's an easy way to remember it. Sulfur 8 oxygen, right? Okay, so if we look at the others, we've got NO3, that's a molecule with a minus charge. Nitrogen 8, nitrate, right? We have CO3 2 minus, carbon 8, you got it? Carbonate ion. PO4 3 minus, that's a phosphorus 8 or just phosphate. And the one we just did, sulfur 8 oxygen, sulfate. Okay, these are the most common larger molecular ions. Okay, these are very common in lab. Okay, and there they are. So sulfate, nitrate, carbonate, phosphate. And as I mentioned, the math works exactly the same as for atomic ions. You add ions of different charges, they add up to 0, and you are good to go, right? So left you a little bit more room this time. Okay, so let's do the names and the formulas for as many as we can do, right? So let's do an easy one first. Let's just do lithium nitrate, right? So lithium, and we can do the math just under here and rub it out later. Lithium's a +1 ion, right? Nitrate, what charge is it? It's a -1, right? +1, -1, good to go. That's lithium nitrate. It may as well have been lithium chloride, right? Because +1, -1, it cancels, okay? Just keep this thing, this is why I like brackets, okay? So in the book, they don't use brackets for one molecular ion. I like to keep them all the time because it kind of says, don't mess with what's in the brackets, right? Just leave it intact. Don't even think about it. That blob, that thing in the side, altogether has a -1 in this case, okay? So let's try the next one. Now, lithium sulfate, careful here because that's a -2 and that's a +1. It could be lithium oxide, same math, right? +1, -2. So that's -2 and that's +1. How many +1s cancel a -2? 2. Lithium sulfate. All right. Now, last one, lithium phosphate. Lithium is a +1. Phosphate is a -3. How many +1s cancel a -3? 3, right? Lithium phosphate. All right. Now I'm running out of room a little bit, so, you know, take a pause, right? Get a piece of paper, try the rest. I'll do the rest on a piece of paper as well, okay? All right. So we've done the lithiums. Let's do the others. Okay, so take a pause if you need to and just try it. Okay, so magnesium, run this down so you can see, magnesium nitrate. Now here, careful, +2, -1. How many -1s cancel +2? 2, all right? Be very, very careful. When you have more than one molecular ion, you need to put it in brackets, and it's like 2 molecular ions. If I didn't have the bracket, it would be NO32, which just makes no sense, right? It's NO3 twice, okay? So that's magnesium nitrate. Again, it only works with 2 minus 1s and 1 plus 2, so we don't put any dies or tris up here, right? Okay. MgSO4. You might like that one because plus 2 minus 2 cancels right off the bat. 1-to-1 ratio, plus 2 minus 2. Magnesium sulfate. Finally, this is one of those crooked number situations, right? So magnesium phosphate, well, let's do the math. That's a plus 2, that's a minus 3. It's like aluminum oxide, isn't it, right? So you got plus 2, plus 3, 3s and 2s, right? So lowest multiple 6. So 2 times 3 is 6, and 3 times 2 is 6. Okay? 3 2s are 6. 3, that's a minus 3 times 2 is 6. Okay, and that's called magnesium phosphate. Okay, fair enough. Now, for the remainders, I'm going to run back over here. If you look here, we got ammonium and lithium. In terms of a formula, yeah, they're different, but in terms of a charge, they're identical, right? So in terms of the math, they're identical. So instead of lithium plus 1, I can do ammonium plus 1, and the math will be the same. So I can do NH4 in a bracket, which is plus 1, and then NO3 minus, right? Plus 1 minus 1. So I'm just swapping out a plus 1 for a different plus 1, and that's called ammonium nitrate. Pause there, give the others a quick go. All right, okay, you're back. NH4, 2, SO4, ammonium sulfate, and finally NH4, 3, PO4, you guessed it, ammonium phosphate. As you get more familiar with this, you'll drop brackets for just 1 molecular ion like they do in the book, but I want to kind of remind you that it's a molecule, and using the brackets kind of helps. Okay. All right, so fair enough. If we go back to our sheet, we've pretty much got everything covered, right? We got the regular group 1, 2, 3, 7, 6, 5 molecular ions. There's just a few weird ones left. Interesting. So they're metals, so on the left of the periodic table, but they're not members of groups 1, 2, 3, like we saw before. They're actually in this center region. This center region, all bets are off regarding fixed charge, right? This is called the transition series. And things in the transition series make ions of variable charge, right? So they can be anywhere from 1 up to, in some cases, 7, right? Okay. And there are some complex reasons why they do that, but we don't really get into that too much in this course, right? So we just have to learn the common, what we call oxidation states or charges of transition metals, okay? So for example, copper is a classic. It makes a plus 1 and a plus 2. Iron makes a plus 2 and a plus 3. Okay, other classic ones, silver and gold generally only make a plus 1. Zinc always makes a plus 2. Okay, so let's look here. Here they are. So we can see gold and silver make a plus 1, as does copper. But copper appears again here with a plus 2. Okay, so copper has 2 what we call oxidation states. Silver and gold only just have plus 1. Okay, zinc, lead, I forgot lead. And iron will make a plus 2, but iron also makes a plus 3, and chromium we're going to throw in also makes a plus 3. Okay, so those are the ones. There's nothing to do with column. Okay, you just got to know those. Okay, so unfortunately that's kind of what, like the harder ones to learn. All right. Okay, now do you see a potential problem? If I said to you, what was the formula of something like copper chloride, right? Okay, and remember, copper comes in a plus 1 or a plus 2, right? So if I said to you what was copper chloride, remember chloride's a minus ion, you'd actually get 2 answers, wouldn't you? You'd have copper with the plus 1 inside and copper with the plus 2 inside. So it'd be CuCl, right? And CuCl2. There'd be 2 answers, right? So it doesn't work like before. Somehow you have to be able to differentiate between the thing with copper plus 1 and the thing with copper plus 2 inside, right? So can you see a potential problem with ions that have 2 or more charges? Yes, there's more than one answer, okay? Which one do you choose? That's the question, right? Well, it's actually simpler than you think, okay? You just name it based on which charge ion you use, okay? So if we look at this one here, the Statue of Liberty, we talked about it a little bit previously, and copper pennies go green, Statue of Liberty has a green tarnish, right? That stuff is Cu2O. That's the green tarnish on the Statue of Liberty. Now if I kind of work backwards, because oxygen's always a -2, right? And then there's these 2 of these things, and they must be +1, mustn't they, to make it all add up to 0. And we call that copper 1 oxide, right? And sometimes we put a bracket around it because it's +1, okay? So it's all about the charge on the ion, yeah? We don't write the math underneath, of course, right? We kind of do it on the side or in our head, right? So Cu2O is copper 1 oxide. It's all about the charge on one of the metal ions, right? Okay, so it's a little bit tricky, so we can do it, right? So let's look down here. Iron 2 sulfate. If you feel confident, pause, give it a go. If not, let's watch the first one. So iron 2 sulfate. Now here, I've told you it's iron +2, right? So it's Fe, that's a +2. Sulfate, if we look on our list, is also a -2, right? So +2, -2, that's good to go. All right, let's run it the other way. Now here, there's copper. It could be 1 or it could be 2, right? And there's nitrate. Now nitrate's -1 and there's 2 of them, so it's -2 on this side. It has to be +2 over on this side. That must be copper +2. So we call that copper 2 nitrate. There we go. All right, scratch that out. Here, go names to formulas again. Copper 1, so we know it's a +1. Phosphorus is a -3. -3 + 1, we need 3 of them. Okay. Okay. Finally, FeCl3. Well, Cl's a -1 and there's 3 of them. So iron is only one of them. It must be a +3, right? So that's iron 3 chloride. Okay. Now, my intention is Sunday today, right? I want you guys to have this finished ideally by Monday night, right? So if you can tell me, this is for extra credit, what is the name of rust? What is the true chemical name of rust? Fe2O3, what is that? It's an iron oxide, right? But what oxidation state or charge is the iron in there? So that'll go in the name, like here, right? It'll be a 2 or 3 because that's the flavors the iron comes in. Okay. All right. Monday. What's that? What's day today? Oh. For some reason my stopwatch has started. 15th. End of the day on the 15th, you're good. Okay. Now, the last thing, acids and bases. Now, acids and bases are special, if you like, special ionic compounds. Okay, and they're special. Why? Okay, so why are they special? Acids, let me make sure. Typically in the pure state, they're molecular, right? Materials that dissolve to give ionic solutions. Okay. Bases are just like salts, right? They just dissolve immediately. Okay, anyway, just a quick thing. Anything with a plus and a minus ion in it is technically termed a salt. So sodium chloride is a salt, not the salt, right? So anything plus, anything minus stuck together is a salt. Sodium chloride is an example of a salt. However, acids and bases are special salts, so they have their special subdivision, right? So acids, they contain, when they're dissolved, H plus ions, right? Or ion, and any kind of balancing minus ion, any anion. E.g., H plus, remember H is in group 1, so it makes +1, right? And Cl minus. When stomach acid dissolves, it makes ions, right? It's ionic. When it's actually in the pure state, it's actually a gas, all right? So that's why acids have weird names. We don't call that hydrogen chloride necessarily. We call it hydrochloric acid because it's an acid that has that dual personality. More on acid names in a minute, okay? Bases, on the other hand, contain the OH minus hydroxide ion, right? That'll go on the back with any cation. All right, classically NaOH would be a classic example. Sodium hydroxide, Na plus, OH minus. Okay, all right. So, recap: acids and bases are ionic compounds essentially. Acids contain H plus. That's what turns them into acids. When you taste something sour, it's the H plus ion sitting on the receptor on your tongue. Okay, more H plus, the sour, more sour it tastes. OH minus is caustic, so draining, cleaner, things like that, right? Kind of dissolves hair and other things. So these are kind of like really powerful ions in terms of chemistry, right? So they're kind of the yin and yang of the chemistry universe, right? Okay, so OH minus on the back makes a base, H plus on the front makes an acid. Now, bases, to be honest, they keep their name. So NaOH is sodium hydroxide, but as we mentioned, acids do have special names, okay, because they have that dual personality. So let's talk about them kind of both and then kind of concentrate a little bit on acids, okay? So, naming acids and bases, okay, now for the first midterm, I don't mind which scheme you use. You can use the regular ionic scheme, or you can use, if you like, the true acid names, all right? I'll give you extra credit if you use the true acid names, okay? But by the time you finish the course, you should be able to kind of know that HCl is hydrochloric acid, okay? Not just hydrogen chloride. So there are two ways of naming acids and only one for bases. The bases is just the standard ionic scheme, okay? Remember, the H plus ion is the hydrogen ion, the OH minus is the hydroxide. So we can just, for now, right, just name them like they're ionic, right? Plus one, minus one, run the names together. Hydrogen, chloride. Bases, always just run the names together. They're ionic all the time. Sodium hydroxide. Okay, so pause, take a minute, fill in the rest. Okay, you're back. Now, that's the way you'd say it in the book, right? But I like to do that. So it's two H pluses and one SO4, 2 minus. Acids are ionic, right? So that's hydrogen sulfate. This one, plus 2 minus 1, two of them. Calcium hydroxide. H plus, NO3 minus. Nitrate on the back. Hydrogen, nitrate. Finally, aluminum hydroxide, OH minus, Al plus 3, aluminum hydroxide. There we go. Okay, so again, for full credit, you can just name them like they're ionic, because when they're dissolved and they're doing chemistry, and that's where we see them, they are ionic. All right. However, acids do have that kind of special dual personality. In the pure phase, they're usually molecular, they dissolve, they form ions, so we can't name them with either scheme. We really have to give them the special name, okay? So, let's think about it. Now, what I suggest you do is just learn one, a very common one, and then just go by analogy, right? So, you may know that HCl is stomach acid, right? And you may know its name as hydrochloric acid. So if I said to you, what's HBr? Chloro becomes bromo, right? So it's hydrobromic acid. So if you know one, you can always work out the others, okay? That's one way to do it. Or you can use the rules, right? So the rules are, if I start with the chloride ion, right? Chloride becomes chloric, and then I put hydro on the front and acid on the back. That's the rules for naming, right? So you can either use one as a kind of an example to work from, or just say, hey, chloride, chloric, hydrochloric acid. Okay, so what's HBr then? You can do it by either method, right? It's hydrobromic acid. Now this only works for ions that have an "ide" ending. So chloride, bromide, also cyanide, also sulfide, right? Okay, so as long as it has the "ide" ending, it's hydroic acid, right? This one, iodide, iodic, hydroiodic acid. This one, weird, cyanide, cyanic, hydrocyanic acid. Finally, sulfide, it's kind of a weird way to say it, but we say sulfidic, right? Hydrosulfidic acid. Okay. Ide becomes ic, hydro on the front, acid on the back. Or just say, hey, HCl, hydrogen chloride, hydrochloric acid, if you like, HBr, hydrobromic acid. Okay. So hydros essentially go with IDE anions, right? When we have the larger anions, right, the larger sulfates, phosphates, and carbonates, it's a little different, right? So it turns out the biggest bulk produced chemical in the world is actually a chemical you own. It's in your car battery, battery acid, H2SO4. That's called sulfuric acid, right? So again, if you learn one, I recommend sulfuric acid. You can use it as a base to work out the others. So sulfide became sulfuric, and we just put acid on the back, no hydro, right? Okay, so that is our example: nitrate, nitric acid, sulfate, sulfuric acid. Okay, so that one, sulfuric acid. Just work out these two here. When you write their names, you go, oh yeah, that sounds familiar, because you know them, right? H3PO4, phosphate, phosphoric acid. Okay, pretty nasty acid. It has 3 protons on it, so that's pretty acidic, right? Also found in Pepsi and Coke. Check your ingredients. All right, H2CO3, carbonate, ion, carbonic acid. There we go. That's what makes Pepsi and Coke so acidic, is well, any soft drink, because if you dissolve carbon dioxide in water, you make that, which is an acid. Okay, there we go. So, you know, be able to name acids either as straight up ionic compounds for full credit, or with their acid nicknames for extra credit. Okay. Now I get to be a nerd for a while, right? So, as you can probably tell, I'm a little older, right? So I'm just over 50 years old when I do this. Okay, so I was alive in 1977. 1977, I was 9, all right? And what changed my life in 1977? The movie Star Wars. And it changed so many lives, it was unbelievable. Because, you know, you talk to anybody in graduate school in the 1990s, why are you here? Oh, Star Wars, right? Okay, so what the moonshot was to the previous generation, everybody went to want to be an astronaut, an engineer, and a scientist because of what NASA did going to the moon. Later on in the 70s and 80s, we had Star Wars, and it was a super huge thing, right? And we all wanted to be scientists because of Star Wars, all right? So now, when I went to see Star Wars many, many years ago, I went to this place. It's called Yeovil Cinema, right? And this is in 1977, right? So there were no multiplexes. I had to drive 18 miles with my mother in a little car, right? I feel like young Sheldon. Right? And then we turn up at this place, which is now a bed shop. It's called Cinema Beds, believe it or not. All right. And this was the biggest cinema for many miles around, maybe for 100 miles, right? And it had, guess what? 3 screens. Yes, 3 screens. And for once in the lifetime of the cinema, all 3 theaters, all 3 screens were the same movie, Star Wars, right? Never been done before. And normally, you know, there's a few people milling around out here in the foyer area. When we went to see Star Wars, there was a line out of the foyer, round the corner, round the back of the theater, across a bridge, down the other side of the street. That many people wanted to see it, okay? So I have a kind of an important question for you nerds out there, okay? What makes Star Wars such a good movie? And what makes something like Battlestar Galactica, which is a pretty terrible movie, but similar in terms of its kind of sci-fi kind of approach, which came out at the same time, right? So Battlestar Galactica and Star Wars were released around the same time. Star Wars went on to be probably now the biggest grossing film of all time, behind, well, it was just behind Gone with the Wind recently, but with all the re-releases, it's probably more now, okay? So Star Wars, the biggest grossing movie of all time. Battlestar Galactica just went straight to video. So why? Right? Why? And if you think about that for a second, it's because of what we call believable special effects, right? So if you think about the movie, think about the special effects. What do? Well, they fight with swords. We've seen a sword before, right? One of my favorite ones is when the guys in The Empire Strikes Back, he's driving the walker and he brings down a periscope to aim the gun, right? That's kind of cool. It's like a submarine, okay? And the hallmark of a great science fiction movie is that you can actually see this happening in the future, right? And to make it kind of seem real in the future, they kind of use reference to real life today. Okay, that's why probably one of the greatest movies ever, in my opinion, for sci-fi was Aliens, right? Because it's so scary, because it just seems so real. These real guns and things like that. All right. Anyway, so back to Star Wars and my nerd fest here. Okay. The best Star Wars movie is, of course, yes, The Empire Strikes Back, okay? And in The Empire Strikes Back, we see this thing. It's called the ion cannon, all right? Now, I'm about to run out of time, so I'll briefly pause and come back. Okay, see you in a second. Okay, we're back. So, talking about the ion cannon, instead of me just sitting here kind of telling you what happened in like 1982 or something, why don't I show you the clip which kind of explains everything? So let's take a look at that ion cannon at the movies.
All troop carriers will assemble at the north entrance. The heavy transport ships will leave as soon as they're loaded. Only 2 fighter escorts per ship. The energy shield can only be opened for a short time, so you'll have to stay very close to your transports.
2 fighters against a Star Destroyer?
The ion cannon will fire several shots to make sure that any enemy ships will be out of your flight path. When you've gotten past the energy shield, proceed directly to the rendezvous point. Understood?
Yeah.
Good luck.
Okay, everyone to your stations, go!
Their primary target will be the power generators. Prepare to open shield.
Sir, rubber ships are coming into our sector.
Good. Our first catch of the day.
Stand by, ion control. Fire.
The first transport is away.
Okay, now was that cool or what, right? So, what happened there? Well, if you notice, the ion cannon did not destroy the spaceship. It actually disabled it, right? And why does that relate as a good science, special effect today? It's because of things like this and things like this. If you ever take your computer down to get repaired, take it to the Geek Squad or whoever, right? The person who repairs your computer will always put this kind of wristband on. It's kind of a metal strap, and they attach it to the desk, right, before they open your computer. So why would the technician tie themselves to the table with a metal cord before opening your computer? Well, it's because if you have a static buildup, right? And you know about static electricity. When it gets cold and you kind of put your key in the door, you get that static electric discharge, right? So think about that. So you open the case of the computer, you go in with a screwdriver, and you get that static discharge into the CPU. That's like a $600 mistake, right? So to prevent that, you ground yourself, okay? And then you don't get that discharge, okay? So static electricity is just essentially iron jumping across a gap, all right? And as shown with the kind of the wrist mount, right? Ions into a piece of electronics will kill it, essentially disable it, right? And that's what happens with the spaceship. The ion gun shoots ions, just like what happens between your key and the door when you try and open it, right? And the electronics of the spaceship were essentially disabled, which is kind of cool. So we see this effect in everyday life, and we see this effect in the movies. Now, I went to graduate school in the early 1990s. I joined my group, the Trinary group at UIC, and I'm starting to work in the lab, and then the advisor comes in one day and he says, I need you to get the iron gun. I'm like, what? You have an iron gun? Yeah, they had an iron gun in the lab, and here it is, okay? So what happens with surface science, which is the group I was with, we basically have a box, and we suck all the air out of the box, and it's just like outer space, right? Because we have to clean our crystals in an ultra-high vacuum. So there's the thing we're going to clean. And what you do, you use the iron gun to fire ions at the surface, and it obliterates the surface. It makes it look like a lunar landscape. It pits it, it makes craters, but it gets rid of that first few atomic layers of dirt, right? And then you heat the crystal up and cool it down, and it forms a nice flat surface. So all those flat surfaces you've seen on STM are actually annealed, flame annealed they call it, in ultra-high vacuum. So that's what we do to clean the surface. So we use an ion gun or a sputter gun to do that. There's a real ion gun, right? That's the one I used in graduate school. All the best ion guns come from Germany, which is kind of neat. All right, now here's a question, right? So would an ion gun be any good for home defense? You hear a noise in the middle of the night, nudge, nudge. So awesome, get my ion gun, right? Get down there with the ion gun. Would it work? Well, kind of yes and no, right? I mean, we kind of have these things already. They're called tasers, yeah? So I don't know if anybody's ever been tased, but if you ever do get tased, they actually have to come up and stick you with the taser. You kind of shoot from a distance, but these little darts are slow moving and they got wires in the back. You have to be in physical contact with the gun, right? That's because you have to pass the electricity around a circuit, yeah? So you can't kind of fire ions through air like in the movie here, right? Because it will go about that far. So there's too much air, it'll block the ions. That's why when you go and like put your key into a door to unlock it and you got that static build-up, it jumps about that far, right? Because that's about the range of an ion gun in air, yeah? So no good unless your intruder's an inch away, right? So no good, but in the vacuum chamber, these ions can go as far as they want. So in the outer space, in the part of the movie where the ions hit the spaceship, absolutely possible. Through the atmosphere, not so much. So that's kind of interesting. All right, now, last page. This one is as close to a real exam question you'll see for ions, okay? So I give you always a list and everybody's going to get like a, a different exam with different ions to choose from. That's the great thing about chemistry. It's, I can very easily create different tests, so you'll get a different test, right? But what you got to do, there's 3 pluses and 3 minuses, so you can make 9 combinations, right? So this is worth 18 points, this part, right? So 1 point for each formula, 1 point for each name. A little bit of extra credit if you give me the true acid name, for example, okay? Point off if you don't get it, okay? So what I suggest you do, if you've got this in front of you, just pause, try and get 18 formulas and names, right? Okay? And then come back and see how I did it. All right, give it a go. All right, you're back. I like to be systematic, right? So all the H1s first. So H plus and Cl minus. Now I'm not remember what I said in the first part of this video. Never, never, never include the charges in the formulas because they cancel. That's the whole point. If you leave them in, it's wrong, right? So that's HCl, no charges there, we can see, right? H plus, Cl minus, they cancel. All right, so that's hydrogen chloride for full credit, or for extra credit, remember? Chloric acid. Okay, fair enough. Plus 1 extra credit for that. Okay. H with SO4, 2 minus. So H plus 1, SO4, 2 minus. There's going to be a 2 there. That's how you'd say it in the book. I don't mind if you put brackets around. That's fine. Now that's a big ion, so that's kind of actually the shorter name. So that's sulfuric acid, right? Or hydrogen sulfate if you want to use that. Full credit. For extra credit, sulfuric acid. The other acid is phosphate on the back, hydrogen on the front. Phosphate's a -3, right? So we would do that first. So I need 3 plus 1s. That's phosphate, phosphoric acid. Okay, fair enough. Again, you could say hydrogen phosphate. That would be okay, but that's for extra credit. Okay, so that's all my compounds with H plus in. Now my tricky one here is copper. It's copper 2. Remember, copper comes in 2 flavors, +1 and +2. So I've got to say in the name the charge of the ion, right? We go Cu, Cl, right? So +2, -1, I need 2 of them. That's copper. What charge was the ion? 2. Chloride. Next one, Cu, SO4, +2, -2. So that formula is good. But it's copper, again, because it's a +2 ion, 2 sulfate. Perhaps the trickiest one would be, well, let's name it, right? We're going to do copper and phosphate, and it's copper 2. So run it backwards, why not? Copper 2 phosphate. So we're told it's going to be copper +2, and we got phosphate, right? That's a -3, that's a +2. It's that whole multiple of 6 thing. So I need 3 of these and 2 of those. There we go. All right. You got to have that 2 there, otherwise it's graded wrong. All right, last one, aluminum, group 3 plus 3, aluminum chloride, 1 plus 3, 3 minus 1s, aluminum chloride. Next one, aluminum sulfate. This one's a little tricky because it's a 3-2 deal, right? So we put the names here and then come back. Aluminum sulfate, that's a -2, that's a +3. So we need 3 of these and 2 of those. Okay. Obviously brackets, if you've got more than one molecular ion, it's got to be SO4 3 times, right? Not SO43, which is crazy. All right. Finally, last one, nice easy one to finish. Aluminum phosphate is nice and easy, +3, -3. Aluminum phosphate. Okay, there we go. So that's the end of the packet. Make sure you get those kind of down pat, so to speak, all right? And you see something very similar on your test. All right. In the back of the packet, there's a few things to look at. Now, I'm not going to have you learn this, of course. I just wanted to show you a cross-section of ions that are out there in nature, okay? So there are literally hundreds of ions. We're just learning a small cross-section, so I'm not having you learn all the ions. There's more out there, but remember your list. Where is it? There it is. Remember that you're only going to learn these ions, okay? And that will be for your tests. Okay, stop there. See you guys in the next one.